Welcome to the University of Southern California and Tsinghua University Faculty Research Symposium on Data Analysis and Informatics. Good evening to all of you tuning in from Los Angeles, and good morning to all of you tuning in from Beijing. Whether you're enjoying some decaf coffee or some green tea, we are so glad to have you. We are going to be showcasing some cutting-edge research from faculty at both USC and THU. So without further ado, please join me in welcoming to the Zoom stage Dean of the USC Viterbi School of Engineering, Dean Yiannis Kouros.
Thank you, Tiffany. A warm welcome to everyone, both here in Los Angeles and the United States, and also in Beijing and China. Good morning to all of you out there. This symposium usually happens either in Los Angeles or in Beijing, and it alternates every year. This is something that started way back in 2007 or 8, if I'm not mistaken. And it was become possible through the generosity of our joint alum, Mr. Fang, who has been also a generous sponsor of this effort to bring together USC Viterbi School of Engineering and Tsinghua University. We are very happy to be able to have continuing this partnership for many, many years now. And I'm happy to see that even a pandemic will not be an obstacle to putting it together. It's a different way of participating this year. And I'd like to welcome and thank all of you who are taking part in this event, which is a virtual event. But as I have said before, even though we are physically separated, we are more connected than ever before everywhere in the world as we are fighting this pandemic, which hopefully we will see the end of it sometime in the not too distant future. A lot of the work that will be presented here today includes obviously mostly work related to how we can use technology and information science and data science in many applications, including on how to address the modeling and also other aspects of the COVID-19. This is something that is important for many of us. As we are also considering the restart of the university in the fall. Many universities in the United States are actually right now are in the process of thinking on how to restart. There are a number of parameters to consider. Understanding more and more how the infection spreads is a very important part, given the fact that, even though the first wave of infections has been in a way diminished, there is always the likelihood of a second wave, and we want to make sure that we are careful about to make sure that our students, as they come back on campus, are safe and healthy, as well as our faculty and staff. What you see from my picture is I'll just remove myself a little bit from my square for a moment, so that you can see the plaza that you at USC Viterbi. This is the so-called Epstein Plaza. It's a plaza that I see from my office, even though I am not in my office today, but definitely it's a good picture. And those of you who have been on a USC campus, you probably remember this and see it, particularly our friends and colleagues from Beijing and Tsinghua. So again, I wanted to thank all of you for being part of this great symposium. I look forward to listen to many of the good presentations. In fact, I had the opportunity to also speak myself. I had during Memorial Day weekend, I had about a couple of days that I was able to dedicate to look at the issue of the contagion. And so you probably, hopefully you will see some of the work that we have done together with my colleague, Asad Oberai, who is actually part of that particular paper as well. So without further ado, I want to give it back to you, Tiffany. Again, I look forward to perhaps next year, having an in-person gathering so that we can see everyone in person and be able to, celebrate our collaborations in different ways as well. So thank you, Tiffany.
Thank you so much, Dean Yortsos. I'm really excited to see your presentation again. Very impressed at how you managed to put that together so quickly while dealing with everything else on campus. So without further ado, I'd like to welcome to the program Dean of the Tsinghua University School of Information Science and Technology, Dean Shanghai Dai.
Hey, dear friends and colleagues from USC and Tsinghua. Good afternoon and good morning, everyone. On behalf of the School of Information Science and Technology, Tsinghua University, I'd like to welcome you to our online 2020 USC-THU Faculty Forum. As you all know, Tsinghua University and USC have jointly organized the Faculty Forum series for more than 10 years by mutually visiting each other and exchanging ideas. This year, we have to change it to online due to the pandemic. I'm sure we will all remember this year's special forum. I would also like to wish you health and safety during this challenging time. As a school dean and the National Research Center director, please let me first briefly introduce the school and research center. Our School of Information Science and Technology, which you may know quite well, is the largest school in Tsinghua University. Which you may know, it consists of 4 departments, 2 research institutes, with more than 450 faculty members and nearly 7,000 students in total. The Beijing National Research Center, BNRC, for Information Science and Technology is one of the 6 national research centers in China, and is the only center in the area of information science and technology. It was approved by the Ministry of Science and Technology of China in November 2017, and its aims exploring future network theory, intelligence science, and technology, and other key directions in the information field. So far, the BNRC has established 6 research departments, including first, future network theory and applications. Second, intelligence science and technologies. Third, advanced electronic and photoelectronics science and technology. Fourth, Chartworth software and big data. Fifth, aerospace information fundamentals. And sixth, bioinformatics. Since this is a national research center, which happens to be located inside the campus of Tsinghua University, it's open to everybody, including colleagues from overseas. I do hope through this Tsinghua USC Faculty Forum, more USC colleagues are interested in know better about the school and the research center. I would like to take these opportunities to invite you all visit in the future. Last but not at least, I'd like to take these opportunities to express my special thanks and appreciation to our common alum, Mr. Deng Feng, who has started and provided his generous financial support to this faculty forum series. We are very proud of and appreciate his generosity and support. Also, I'd like to express my sincere thanks to Dean Yiannis, who has been leading and steering the faculty forum from the very beginning. I strongly believe that Dean Yiannis will continue to lead us to strengthen the friendship between Tsinghua and USC. Of course, myself will closely work together with Yiannis. Thank you very much. Wish the forum greater success. Thank you.
Thank you so much, Jindai. That was wonderful. What a great partnership. Thank you so much for being here today and to help us coordinate. Now I would like to welcome a special guest to the stage. Fang Dang is the Managing Director of Northern Light Venture Capital and a USC Viterbi alumnus. Fang, thank you so much for joining us today. Do you have a few words for us?
Thank you, Tiffany. Dear Dean Yiannis, Dean Dai, dear Professor Raghuventure and Professor Wang Yu, thank you for having me here. I'm so glad that I can participate. Actually, the one thing that we can do it with this virtual format, it's easier for me to participate. It's my honor to sponsor this for the last, actually I counted, it's about 12 years, right? This is the 12th year. It's just, I think, this year is very different than all the previous years, right? Not only because of we do it virtually because of the pandemic, but also at this time, we're having a lot of challenges, especially between US and China, a lot of tensions there. I actually think that, at this time, doing this has a different meaning. We have seen a lot of collaborations between USC and Tsinghua, a lot of results coming out of this symposium and interchanges between students and faculties. And this actually, demonstrate how important it is to collaborate in the academic world for education and for research, right? And I think right now, under this current tense China and US relationships, USC and Tsinghua has done a great job, and we shows to the world that this is important to continue this collaboration, and globalization is so important, not only for the two universities, not only for the two countries, but also for the human beings. So actually, I think I'm glad that I can be a sponsor for such a symposium, and I'm actually thinking we should continue to do this for the next, I don't know how many years, but let's continue to do this. I hope this symposium will be successful, and I hope everyone will be safe under the current pandemic, and I hope that we can see each other, have face-to-face meeting next time. Thank you.
Thank you so much, Fang. I think what you said is very profound. Now is the best time, the optimal time for collaboration between our schools and our countries. So thank you so much for saying that. Now we will begin the technical presentations from our featured speakers today. After each presentation, there will be time for a brief Q&A from all of the speakers. So when you think of your questions throughout the presentation, please enter them in the Q&A chat box, and the presenters will answer them as soon as possible. Now, without further ado, I would like to welcome back to the stage, Dean Yiannis Kouros.
Okay, hold on. Can you hear me?
Yes.
Okay, so let me see why. Okay, here. Okay. I was able to get back here. Let me just okay, let me do that.
Fantastic.
So let me share my screen and okay. Just one moment. I think I need to do one more thing and then I'll be back.
Great. And just so everybody knows, Dean Kouros will be presenting on a comprehensive spatial-temporal infection spreading model with applications to COVID-19.
Okay, I believe I am almost there. Sharing my screen.
Perfect.
Can you see it now?
Yep, we can see it.
Very good. Okay, so thank you all again for for this wonderful opportunity that I have to present here. Thank you again for your support. I didn't get to see you, both of us at the same time in person. Our images where we are alternating on the screen here. But I wanted to thank you again for the support that you have been providing all this time in getting this program together. By the way, this year the expenses will be a lot less than before, Fang, because it's all digital. So we have money to take it for the next year as well.
Yeah.
And many more years to come. So you should feel very good about that.
Staff time, Yiannis. Don't forget the staff time.
Oh, staff time. Okay, I'm sorry. Okay. So as I mentioned before, I have been thinking a little bit about how we can take the SIR model, which is a well-known model for the spreading of infections, and try to actually add, in addition to the spatial dimension, the temporal dimension, a spatial dimension. I have been exposed to this model maybe around April or so. And then I was trying to think about how to make it perhaps a little bit more applicable to more general conditions. And so I think I had about a weekend free during Memorial Weekend, and I sat down to see how we can perhaps look at it from a different perspective, which is the perspective of a chemical engineer. I am a chemical engineer, so I'm sort of a more familiar with the modeling of chemical reactions, and that include also transport and diffusion. And when I was looking at the various models that appear in the literature, at least at the beginning, they were all based on simple models that did not include any of the special variation of densities and so on and so forth in space. So we put something together, and then I worked together with my colleague Asara Oberai, who is the Vice Dean of Research, and also we'll say if you make some presentation here as well, and together with me after we go to simulations, and his student Hari Shankar Ramaswamy, who will also is contributing in creating some of the simulations here. So this is an equation-heavy slide, but I think it is necessary to set the stage for what we're trying to model here. So the fundamental assumption of the so-called SIR model is that it has three species. And these species are, in terms of people or populations, people that are susceptible. These are people that are not infected yet, but they can be infected. This is indicated by subscript S. People that are currently infected, and they are indicated by subscript I. And people that have been recovered, they were infected and recovered, and R is the subscript for that. The recovered people also include people that died or perished. In this particular model, there is no differentiation between people that recover and are alive or people that died. I suppose one can develop a mortality associated with the recovered part to deal with the ones that perish. But recovered is, this particular model consists of these three species. Now, when we model reactions and transport and things of that type in chemical reaction engineering, the most important variable is what's known as concentration. In this case, would be population density. Concentration is, let's say, gramamoles or moles per unit volume, and in this particular case, the equivalent will be number of people or number of species per unit area, because clearly, the key parameter here is the area over where people congregate. So number per unit area is a population density. In fact, many of the things that people are using in order to enforce various policies deal with the number per area. And this is essentially the spatial distancing, for instance, that's associated with that has to do with numbers per unit area. It has been surprising to me that when you go to the literature, the classical literature for the SIR model, they don't talk about number per area, they simply talk about numbers. And so to us, it's very important that we start from the very beginning by using this particular variable, which are the concentrations, the equivalent concentrations is number per unit area. The first equation to consider is the equation, a conservation equation. So this is written for each of the three species, the susceptible, infected, and recovered. And typical equations look like this. They have a temporal term. This is the rate of change. Then there is a term that has to do with transport of the species in and out of the particular volume that you're interested. And this is by an imposed velocity Q. So in this particular case, Q could be, for example, transportation by trains or by automobiles or by other ways that you go from one place to another. On the right-hand side, there is a term that has to do with the way by which people diffuse or disperse. So this is the gradient of that particular flux, which is a diffusive flux. And there is a reaction rate term. So in the case of a reaction rate, which is, let's say, if you have susceptible numbers, if I apply this for the susceptible population, the reaction rate is negative because it means that the number of people that are susceptible decrease because they become infected. If I apply it for the infected people, then this number here will be positive because the reaction rate, which essentially mean how many people, the reaction rate for the corresponding infected people. And so you write these equations for these three species. So this is three partial differential equations. And then the question is, if you add the three of them, then you have an overall population density, which should remain constant. And this particular number here expresses the total population divided by area. And we will call this in the traditional nomenclature as rho, the density of people, in this case, density meaning number of people altogether divided by area. And that's a corresponding flux. I mentioned that one way to express the dispersive flux or the diffusion is through a gradient. So in this case, we take this to be the gradient of the concentration. Whether this is true or not in how people disperse or diffuse is unclear. So for us, it's a conjecture. Potentially, we can use a different type of model for diffusion or dispersion or things that are other than simply an advective term that is imposed in the movement of people. Also, this may not be typically you may have diffusive fluxes or dispersive fluxes that are not equal to Brownian motion that we have in molecules, but perhaps this is something much more complex. Some people talk about Levy flights or fractional Brownian motion in which the steps that you take are not random, but they're correlated to each other. But we're just going to leave this for the moment as simply a typical diffusive flux. The next step is to model the kinetics of this reaction. So we apply what is known as mass action kinetics. And mass action kinetics says that the reaction rate is proportional to the product of the two species, in this case, the susceptible and infected. And this is how people get infected, by bringing infected people with non-infected people together. This product here is the reaction rate, and this generates the rate by which you have to put in here in order to see how things are changing. And we put a parameter K, which is here, or kappa, which is a constant, and has dimensions of time inverse and concentration inverse. And then there is a rate by which people recover. So this is typically taken to be about 14 days or so, or maybe more. And this has to do with the way by which people that are infected recover, or people that are recovered again in numbers as well. And so essentially this completes the formulation of the problem. There's some important notes that come from this simple formulation here. First of all, as I mentioned, lambda is inverse time, is the intrinsic rate at which, on average, infected individuals either recover or die. And one obviously could make the model much more sophisticated and put demographics, people that have, let's say, different age groups and health conditions, maybe reacting at a different rate. And so in a more fine-grained model, one can actually put more populations. The goal of this study is not to do this type of very sophisticated simulation, but rather to figure out some of the important aspects that otherwise you can see by simply looking at the standard SIR model. The most important parameter is the parameter kappa, which is the inverse time and concentration. And essentially, this is the reaction coefficient that says what's the reaction rate when you have two populations that come together. And so this includes the frequency by which people come together. So it could be, for instance, a mean-free path and a collision of that. The contact rate between people, let's call it a collision. And one can use, for instance, theories from ideal gases or even not ideal gases, like Maxwell-Boltzmann statistics, in order to understand, for instance, how these collisions take place. And one potentially could create a function for this kappa, which is an increasing function of the density of the population density, up to a certain maximum packing, which is the closest distance people can get together. Also, if you do it this way, you can also understand that the spatial distancing limits that says that the rate of infection actually goes very low or decreases below a certain density, which corresponds, let's say, to 6 feet. So we expect that this parameter K or kappa here is 0 if the density is less than a limiting density, which is, let's say, the spatial distancing, or it is a function of the increasing function of the density up to a maximum packing distance, which will correspond to this particular density. And so one can take characteristic values for this, can take, for example, ρ0 to be 0.1 meter square inverse, and ρ1 to be 1 meter square inverse. So one can play with these numbers and then see how the corresponding density affects the spreading of the infection and all that. So I think this is very important because there are a lot of area-wide averages that are published, let's say for states or for countries, but actually that's actually a very misleading average, because you have to differentiate between high density places, for example, urban areas, stadiums, schools, retirement homes, and so on and so forth, from low density, let's say suburban or rural areas. I think the more appropriate way to define the problem is to differentiate between these areas, and all of this differentiation has to be enters into this density raw, because this density tells you whether you are if you are in a low density area, then this rate of infection will be very small. If you are in a higher density area, then you can have parameters that depend on the density itself. So that's one thing that you learn by looking at this from a chemical reaction engineering perspective. We also assume that an infected individual can infect a susceptible one at the same rates. We know that that's not necessarily true. You have asymptomatic cases. You have cases where infected individuals have to be quarantined or treated. This particular model doesn't capture this, but it is not very difficult to add this particular component if we wanted to. Finally, I wanted to say a few words about this diffusion coefficient. If you assume a completely random walk, let's say you're on your office and you work in your office, I think one can estimate a parameter for this diffusion coefficient, and my estimates are of the order of 10 to the minus 3 meters squared per second, which is about 2 orders of magnitude larger than molecular diffusion in gases. So, I'm taking this analogy between gases and people, molecules and people, to a certain extent. I'm sure that it's not really accurate at some point, but it's actually an interesting way to model how this disease is going to spread. So if you put it in a dimensional notation, then you can essentially have to solve 3 differential equations, partial differential equations. They involve reaction over here. The reaction rate has this parameter R0, which is a well-known coefficient. But what's important here is to notice that this depends on density. So you can make this parameter go to 0 if, let's say, the density is below a certain number, for instance, corresponding to spatial distancing that so many people talk about. And that's actually something that comes immediately from this particular formulation. You can have diffusion, and you can have also advection. And the advection can be imposed by an external mechanism as well. So these are parameters. We can solve these equations that depend on the spatial density. And we'll show you some examples. I think my colleague Asad Oberai will show you some of the simulations in a moment. So you can simulate a number of things. So one of the simulations is the typical constant K, no entry or exit, in or out of the system. It's like a batch reactor model in chemical reaction engineering nomenclature. This is a standard SIR model where everything is well mixed. You put everything inside, you start the time t equal to 0, and then you get it going. One important thing, however, that these models don't consider is the importance of fluctuations. So for instance, they take that, because the reaction rate is proportional to the multiplication of two concentrations, S and I, the SIR model assumes that the average of SI is the product of the averages, but does not count for the fluctuations. So it is very, very interesting to see whether this average of the fluctuations, of the product of the fluctuations, contribute to the effective reaction rate. And that's something that we're trying to understand. And this can only be possible if you allow for fluctuations and then have effective diffusion as well. So that's an important parameter to enter into your equation, because the more fluctuations you have, the more inaccurate will be equating this guy here with these two parameters. Another policy to simulate, case to simulate, is to enforce health policies after an elapsed period of time, let's say spatial distancing or lockdown. And this is something that you can easily put in this particular model. To have entry in the system for a finite time and constant K, let's say people have been talking about imported infection. What comes into, let's say you are in a situation in which you have a community that has 0 infections, but then you import an infection because of the arrival of certain infected people. So this is equivalent to what is known as a CSTR model in the chemical reaction engineering nomenclature. And the question is, how, if you were to bring in some infection, how this grows in time and corresponding to that. And finally, spatially variable interactions and the effect of diffusion. So I like now to stop sharing and give the screen to my colleague Asad Oberai, who will then show you some of the simulations.
Thank you, Yiannis. Thank you very much. So I'll take off where Yiannis left, and if the host can please give me, let's see. Yeah, I do have the ability to share. So I'm going to start exactly from the slide that Yiannis was showing and just walk you through some of the simulations that we've done together. So the first set of simulations is where we're going to assume spatially homogeneous conditions. So, it's a domain we are modeling where everything is the same. So the density is the same. And in particular, we are looking at the number of susceptible, infected, and recovered population as a function of time. And we are looking at this for a disease which could be considered very virulent. So R0 is 5. And we've non-dimensionalized time here by the time it takes for the disease to wash out. So 14 days. So 1 unit is roughly 14 days. And we start out with an infection rate of 1%. So 10%. So 10% of the people are infected, and we let the simulation go, right? And what you see is that within 14 days, so within 1 unit of time, infection really rises very steeply. So there's hardly any time to react, and reaches a peak of about 0.5, and thereafter starts decaying. And sort of consistent with that, the number of susceptible people, which was 90% here, drops precipitously and then reaches almost 0 by the time the simulation ends. And you might imagine that all those susceptible people have now been infected and as time goes by have recovered or passed away, and they're both sort of included in this bin. And that almost reaches 100% by the time by the time this disease is progressed, right? So that's this case. But you might say that, okay, you see that the infections are rising and very quickly. So within maybe 2 or 3 days, you institute a rule where you do physical distancing, and so all of a sudden you bring the density down, the effective density low. What is going to happen then, right? So we assume that. So after 7 days, the effective density is brought low through physical distancing, and then the reaction rate sort of goes from 5 to 0.5. And of course, this also happens at a non-dimensional time of tau equals to 0.5. And you can see very quickly you gain control of the infection rate instead of going all the way to 0.5. it drops rather steeply, and it takes about a month or so to wash down to almost zero. And what's happening is the number of susceptible people was decreasing till before this policy was in place. It sort of continues to decrease because people are still infected, but at a much slower rate. And the steady state now contains people who are susceptible, who've never been infected, a mixture of those, and then a mixture of others who have recovered from the disease. So this is the herd immunity that people talk about, right? So you've sort of reached herd immunity for this particular reaction rate. And so this will be the steady state, right? So that's the effect of introducing a policy. What if you lift this policy, as is happening in many states and many regions, at least across the US at this point? So maybe, after about 14 times 7 days, you lift the policy, the number of infections is very low. Well, what's going to happen? So let's say the reaction now rate goes from 0.5 back again to 5. Well, what's going to happen is what you might expect. You'll get a second wave of infections, which will not be as steep as the first wave, right? But there will still be a pretty significant drop in the number of susceptible people who will all get infected. And you will now reach a steady state of about, I would say 7 or 8% who are susceptible, who've never been infected, and all the others who've been infected. So the herd immunity here is much more towards the side of people who have recovered rather than people who are susceptible. So as Yiannis was saying, you can do many other things here. You can sort of say, what's the effect of a vaccine? And take one population and shift it on the other side, and so on and so forth. But more interestingly, I think it's worth looking at the effect of spatial distribution, particularly in this case, the effect of diffusion. So as people interact with each other, what happens? So we did 2 simulations. The one on the left has no diffusion in it. And what I'm plotting here is a Gaussian profile of infected people. So you can think of this as space, right? So this is space. If we're looking at a city or a state, and uniform density, and we have a Gaussian profile of infected people. And this, I think, rises to about 20%, right? And it's a Gaussian profile. And so the question is, what happens in this case? Well, what's going to happen is, as I play this, more and more people will get infected, and this will propagate outwards because people who were way out there, where there was a very small infection rate, if you give them enough time, the reaction kinetics are such that even they will get infected, except it will take a long time for them to get infected because they're starting at a much smaller initial state of infection, right? So it will eventually get there, but infinite time. So this front will slow. And what's also interesting here is in the middle, you see a low infection rate, but that's basically all the people who've been infected now. And that all those people are not infected anymore. They've recovered. So they've been moved to the sort of the recovered bin, right? And so that's what happens when you don't have diffusion. So now in addition to this, if you add a little bit of diffusion, it's not a whole lot of diffusion, what happens? Well, the dynamics is very different. The dynamics evolves very rapidly because of diffusion. What happens is that, the initial state of infected people almost at every point rises quite rapidly because of diffusion. So people intermingling with each other. And this disease, which took a long time, it's interesting to actually get these both started at the same point. So maybe I can try doing that there, which took a long time to propagate, propagates much faster now. So these are the kinds of things we are using this model to try and understand what the effect of these parameters are. We really aren't at the point where we're trying to quantitatively predict and match with data, but we are trying to understand trends of what's going on. And I should mention that these simulations were all done by a graduate student at USC, Harishankar Ramaswamy, using a finite element code. Thank you.
Thank you so much, Professor Obrai. All right, so I think we have just a couple minutes for Q&A, and I'd like to actually toss this over to one of our faculty members who has the first question, Professor Raghu Raghavendra.
Yes, nice presentation, Yiannis. It was good. The analogy is good comparing the molecules to people. However, in the mobility movement, the molecules follow some physics laws and you cannot know that thing, but people is more like a social thing. But so some kind of a mobility model need to be used for that. Like we do in mobile computing or wireless networks, some kind of mobility model might give idea of how they move around. So any comments on that?
Yes, actually, thank you, Raghu, for mentioning that. It is a fascinating way by which you can, so the model that we use is essentially a typical statistical thermodynamics model for, let's say, gases or liquids, in which molecules collide with each other. Maybe they have some interaction of forces as they collide, but most of the time their movement is random or maybe correlated in some way. But a number of way by which humans move around. Maybe we're talking actually with Professor Victor Prasanna earlier today. Maybe one way by which we can model the movement of people is by creating, let's say, some sort of a potential energy landscape of which the gradient then provides a force. And then based on the mobility of that it has a corresponding velocity, and this, based on this velocity, then we can move people around in a different way. And I mean, I think the domain is open for many interesting interpretations and questions. I know that many different approaches to this are done through potentially using network theory or lattice models as well, or maybe agent modeling, where you can get a lot of the you don't make the specific analogy with let's say statistical thermodynamics that you use in the case of gases and liquids and the like. Yes, we are not molecules, even though we are a bunch of molecules, if you think about it, but certainly the molecules that consist people are not indistinguishable as a molecule, let's say, in an ideal gas. So clearly a lot of differences there. It's kind of interesting of sociodynamics, and how do you use them in a different way. I find this to be a very fascinating subject, and I'm sure a lot of people have done interesting work on how you can model behavior of people through modeling, mathematical modeling, borrowing concepts of physics, statistical physics, and the like. Clearly, this happens in economics. People do a lot of statistical model for economics, and there's a branch of physics called econophysics, which in some sense tries to reflect that. I don't know if Asad wants to say anything on this.
No, other than to say that it's very complicated. No, nothing else.
People movement is very complicated. Yes, thank you, Yiannis.
You're welcome.
Great. We actually had one question last time that was really interesting that I think would be, fascinating to answer here. But because there are certain cases where a person is infected, recovers, and then gets infected again, because of the recovered people would be a subset of people getting infected, would the process of getting infected again create an ambiguity for a person's species in a certain area?
Well, definitely a good question. The answer is that this particular model, it's very simplistic, doesn't capture people that can be reinfected. It's not difficult to have these people as well there. I'm not sure that we understand the biology and the rate of infections well enough to be able to say, whether people can be reinfected. So the best way one could do this is to say that the fraction of the people who have recovered potentially can be infected, and then just use this as a parameter to see how this affects things. It's possible. I think that we don't know yet a lot about this particular disease to figure out whether people can be reinfected or not. I think there have been some incidents in the literature, but I'm not so sure that this is a well-known fact, an established fact medically yet.
Fantastic. Well, thank you both again so much for presenting, Professor Oberei, Dean Yortzos.
Thank you.
Thank you. Now I would like to welcome to the stage our next presenter. Yang Li is the tenured associate professor of the Department of Electronic Engineering at Tsinghua University. His research interests are in the areas of data science and data mining. And Dr. Li today will present to us his research on urban epidemic modeling and control with human mobility. Thank you so much for joining us today, Dr. Li.
Yeah, is my voice clear?
Yes.
Okay, yeah. Good morning and good afternoon. It's my great pleasure to introduce our recent work about the area of urban epidemic modeling and control. I'm Yiannis. I'm from the Department of EEE, and actually, the background of our research is that we are trying to find the epidemic modeling with the human mobility, how to conceive the human mobility into the epidemic modeling and control problems. Actually, the background is that COVID-19 has become a global concern that affects most of the countries. And we have a lot of questions like when will the disaster end, and what should we do to bring this day earlier? Or like even in some countries already have, or cities already have better control, but sometimes sudden things usually happen. And from a very toy games aspect, that should in this, we can find that the key problems we need to understand is how human interact with each other in the city, and to understand further to understand the spreading process between the people. And moreover, from aspect of a global city, like a city connected with each other, and
I think we're having some sound difficulties. Can we try again, Dr. Lee? Oh no.
that
Okay, you sound
we
good
have
now.
several problems here. Need to understand. First one is we need to understand. We need data about human mobility to simulate or to model the epidemic spreading. And the second problem is that after we have the data of human mobility, and then we can use the mobility data to simulate or to model the spreading process of the epidemic.
Also,
and finally, we have
Professor.
you have such kind of models, then we can design some smart control policy to try to control the systems.
Excuse me, can you put yours in the slides in the slide mode?
Wait. Oh. 好，我看一下。Sorry, some problem with my slides.
Click on the slideshow mode. So it looks bigger, the slide, if you put it in the slideshow mode.
Is it okay now?
Perfect,
Sorry.
looks great.
Can you show my slides of full screen?
Yes, we can see it full screen. Perfect. Okay, Dr. Lee, are you going to share your slides again?
You are fine, Dr. Lee.
Dr. Lee, are you able to share? Perfect. Okay, looks great.
Excuse me, can you hear me? Or the screen, the slides is showing okay?
Yes, it looks good. Perfect.
Sorry, I can't hear anything actually. Maybe I need to quit the Zoom and join again. Yeah.
Okay, not a problem. We can actually move on to the next presenter first, if that works.
Okay.
Okay, fantastic. So we can actually move on to the next speaker, and then Dr. Lee, when you come back, we can have you go on again. Does that work? Okay.
Okay.
Fantastic.
I will let them know. Yeah.
Okay. Raghu, does that work?
That will be fine, yes.
Okay, fantastic. Well, in that case, I would love to welcome to the stage Victor Prasanna. Dr. Prasanna is a professor of electrical engineering and professor of computer science here at the USC Viterbi School of Engineering. He also serves as the director of the Center for Energy Informatics. His research interests include high performance computing, parallel and distributed systems, reconfigurable computing, cloud computing, and smart energy systems. Dr. Prasanna will speak to us today on machine learning to track the spread of COVID-19. So welcome, Dr. Prasanna. And thank you for joining us earlier than intended.
Yeah, that's fine. Tiffany, okay, fine. So let me share my screen. Can you see my screen?
Yes, perfect.
All right, okay, let's get started. Thank you, Tiffany. So I will talk about some of the work we are doing in the context of modeling the spread of the COVID virus. So this is a joint work with one of my research associates, ioTBD. We do have a couple of publications. I'll talk about it. So a lot of this work, you can look at it from my website, dslab.usc.edu has all these details of the work as other ongoing projects we have in the group. So we do have a couple of publications. I encourage you to look into it if you are getting more details of what we are trying to do in this. Both of these publications are available on the archive website. The first one is talking about how to do this forecasting. That's what I will talk about today in detail. The second publication listed here is also available on archive. And this is more focused on, given that sometimes we do not have the exact data is about the unreported cases we have, what is the impact of that on the data-driven modeling? So we come up with some performance bounds as to what happens given that we are able to only understand what is reported cases. So we do have some techniques by which we can look at the distribution, the time series. Based on that, under certain conditions, we can give some upper bounds on how much of the unreported cases that actually may be in the system. So we can get some performance bounds based on measuring what is reported and the behavior over a time series over a period of time. And we also give some bounds as to how accurately we can do given a certain amount of time series data is available to us. I will also talk about a particular tool that we have developed working with some of the undergraduate students here on campus. Again, that tool is also available. I'll give some pointers to it. Just to be careful about this particular tool involves certain technical background knowledge here when we use these models, train those models. So it is important that these models are carefully used in the context of where it is intended to be used for us to be able to make these kinds of predictions. Moving along. So I've organized this talk to just a little bit background about what we do in my lab, look at some of the earlier work in this context leading up to the kind of predictions we do in this particular problem that we're looking at now. Following that, I will go into the model that we have developed for the prediction. Specifically, what we do in this model is to look at the impact of travel, and then can we explicitly model that in the particular coarse-grained model that I called about that we have developed here. Also, in this particular model, we also take into account the various states a particular infected person could be in. So we create a number of states. For example, in this particular case, it is believed that up to 14 days, we may have to quarantine a person if the person is infected. So we'll take into account what is the rate at which a person in those states can propagate this epidemic. And that's how this particular model is defined. So I'll go through the model. In particular, we are focused on how do you learn these parameters in this model. I'll go through a particular technique to learn this model and then also give some initial results that we obtained in that context. So finally, I will have some comments to make about how machine learning techniques are used, what kind of parameters we are able to learn, what kind of opportunities that exist in this context for us to be able to use these techniques. So I'll have some concluding comments to make in that context. Following that, I will have some details of the visualization tool that we are developing, go through some details of what kind of visualizations you can do based on the work we have done as part of this model. Just to give some background about the kind of work we do in my group, we have been looking at various machine learning optimizations and applications in this context. I'll go through a couple of examples. One of the problems that we're looking at this time is to look at system design by using machine learning techniques. So one of the problems here is that, for example, if you have a large complex data center, for example, and you want to understand what are the various access patterns that comes into picture so that you could optimize the performance of the system in terms of memory access patterns. We are working closely with Google as well as with Intel and the National Science Foundation to be able to make these kinds of predictive models. So all these problems are in the broad space of predictive modeling. I'll go through a couple of examples leading up to the particular model that we developed for the COVID forecasting problem. Just to be clear about what we are trying to do solve in this particular problem, we are focused on prediction. That means we are making a statement about the future event. And this could be short-term or long-term. Obviously, what is short, what is long depends on the particular application you have. For in our particular case of COVID prediction, this could be short-term, could mean that like I would like to do the prediction over the next, say, couple of days or the next week, few weeks or so. And also that if you predict over a longer horizon, a larger horizon, then the uncertainty increases in the model. Accurately be able to say 1 month from now what happens, that is a harder problem than saying something that what happens over the next few weeks, for example, next couple of weeks, for example. So the short-term and long-term predictions have their own challenges in terms of the accuracy we can get here and how effectively the models can be adapted based on the various conditions that leads to the model accuracy or the errors that may be in the predictions. Let me go through some examples of prediction problems we have been looking at in my data science lab. This is a lab that is focused on applications of machine learning. This particular problem is looking at smart power grids. We have a classic problem here that we want to be able to predict within, for example, by tomorrow at this time, what the power dissipation requirements are going to be, for example, in the Los Angeles area or a particular substation you have. So you want to be able to accurately model this for various purposes, including resource management. And a particular observation here is that there is daily periodicity in this consumption data. So based on this, we can define accurate data-driven models. Therefore, we can define different models for different days of the week, different time frames you have, and then we can combine those models. And again, these models can be defined so that we can adapt these models by using data-driven techniques. For example, we could use specific machine learning techniques here, kernel regression techniques, for example, and then use those models, combine those models, for example, that's what is shown here as an ensemble model. And also when we combine these models, we need to learn these parameters that we are using here, omega 1 through omega t, I'm showing here on the right-hand side. So we learn these model parameters and use that information to be able to predict the actual value of the power dissipation, power consumption at a particular time, given prior data up to that point. So what I'm showing here in the experimental results, some results we conducted as part of the Los Angeles area smart grid project, showing that if you consider the MAPE error or the RMSE error metrics here, by using these models, by using the ensemble model, we can reduce the errors that you have in the prediction problem significantly compared to by not using these single models for in those implementations. In particular, we can bring the error rates from 5%, which is state of the art, to less than 2% in those implementations by using these ensemble models. Moving along, there's also some other problems we looked in the context of the smart oil fields. Again, a large center running at USC, sponsored by Chevron Corporation. One of the classic problems in this space is that given a large number of wells, to be able to choose where do you want to inject steam into the well so that we could recover more hydrocarbons in the process. This is a classic problem in smart oil field operation. And one of the techniques we developed here is to use for deep neural network models here to be able to automatically extract the features to be used here. Using those features, make the kernel regression on that to be able to predict what is the potential gain in doing so. This is a complex problem given that there are thousands of wells in an oil field. And if you were to ask the question, give me 50 wells which has to be chosen for doing the steam injection, it is a computationally very demanding problem. So we are able to solve such complex problems by using deep learning models applied in the context of time series analysis. And what I'm showing here in the results is that by using automatically generated features, by using these auto encoders compared with the manual features used in these regressions, we can get very highly accurate prediction in terms of which wells to choose, And then using that, we can dramatically improve the productivity of those wells. On the average, we were able to get 176% improvement in terms of the recovered hydrocarbons compared to what currently we could do state-of-the-art techniques by using other neural network models. That is almost 40 to 50% improvement compared to state-of-the-art. So one more example here of another application of prediction, something that is very useful now is given that the internet traffic is changing, perhaps, for example, people working from home, we want to be able to rapidly understand what are the traffic in the backbone router of the internet. Again, we want to be able to do this very quickly so that we can make some resource management routing decisions, for example. One of the techniques we developed here is by using LSTM models, which are widely used models in machine learning applications. We use these LSTM models to be able to very accurately predict. And then we combine this model so that we can understand at the router what is the traffic flow at a particular point in the backbone. And then when we combine these various models that we developed, we also use machine learning techniques here to be able to understand what are those combining factors, the weights to be used in combining the various models to get an ensemble model. Using that, we were able to get very accurate predictions of the traffic, less than 10% error on the average compared to state-of-the-art. This is significant compared to the typical ones, which take 20 to 25% errors, what has been observed by using other techniques in the literature. Let me move on. So what brings us to the current problem in the COVID challenge, COVID prediction, is some earlier work we did with one of my students here, Ajitesh Srivatsava. He participated in the particular DARPA challenge in 2015 timeframe, which was focused on understanding, given travel data in the Americas, can you predict the propagation of chikungunya virus in North America? That was the specific problem. So we were given travel data at that point, also of population in the various counties, various states, various countries where the traffic originates. And we were asked to create models. And so this was a particular work we did at that time to be understanding what is the impact of travel on the spread of a particular kind of virus in the system, including some properties of the particular kind of biological properties of the particular virus at that time. So he did an interesting thesis, is currently my research associate. The work I am presenting next is actually carrying on from this work here to be able to understand what is the impact of travel and how can that be modeled in the context of the propagation of the COVID spread. So let me focus on the specific model we have here. So before I go into this problem of forecasting, this is part of a larger project. We are working with the National Science Foundation funding. And here we are focused on first making this accurate models at a fine grained level. We want to be able to understand what is the impact of travel, for example, on this spread, and then use this information to understand what are the ways by which we can come out of the current lockdown situation we have. For example, you want to understand if you open certain businesses, what is the impact of that on the spread? So the particular model that we have developed, we can change the parameters in the model. We can learn those parameters. We can relate those parameters to various mobility patterns we are observing in the system. So we can use our model to be able to understand the impact. That means we can make something like a what-if scenario analysis and use that information to understand what is the impact of a selective opening of businesses, for example. So we can solve a number of such problems by having a very flexible model, which explicitly models, for example, mobility across various agents you have in the system, and also taking into account what is the rate at which a particular infection is spreading. So that will be very useful for us to be able to understand the larger problems of resource management when we go beyond just the initial mapping that we are performing here for the particular flow here. Just to give a high-level view, there are a large number of models. This modeling problem in this space has been studied almost over the last 100 years. The particular type of modeling we are doing here is what I call generative models. Inside that, there is an SI model that we are going to be using here. The particular model that we developed, I call this SI-KJ alpha model here. And this particular model, what is shown here, has 3 parameters, KJ and alpha. I'll define these parameters. And then once we have this kind of a set of equations to define the dynamics of the system, we use the various techniques from machine learning to be able to approximate certain parameters you have in this. And then we use weighted least square to be able to understand these parameters. And then we also do certain hyperparameter selection in the training process so that the accuracy of the results of the prediction are going to be good for our requirements. So we will talk about this model and then talk about how do we use the model to be able to learn the parameters as we go along by using the various approximations we do in the process. Again, just to very briefly go through this, this was also talked about earlier by Yiannis and also by Assad about these models. These are the standard models in the literature. I am using this SIR model and the SI model here, and then showing that these models can be generalized so that we take into account the particular features we are facing in terms of the COVID spread, in terms of the impact of community spread, as well as what happens inside this particular epidemic. Also taking into account the role of mobility in the overall modeling system here. So going into the details of this model, I call this particular model the heterogeneous infection rate with human mobility. These are two keywords in this model here. The infection rate in our model is explicitly modeled in the sense that a particular infected person could be in various states. For example, to a broad extent, there's an understanding that up to 14 days, the infection could be in a person. It may be or may not be noticed. And there may be particular rates, a particular person may be spreading those infections. That's what is a heterogeneous infection rate. I refer to that in the model. Also, that what is explicit in this model is the human mobility. When people move from various regions, we want to be able to take into account the impact of that. And these are the two important variations we do in this model, the SI model that I talked about earlier. And that gives us the more, in my opinion, more accurate model here to be able to model the infection rates as well as the mobility in the system. So in our model, we start with various regions. The C1, C2, C3, C4 are the various regions. F is a factor that takes into account the mobility between the regions. And then we absorb that by this parameter delta, which impacts the various states. A particular infected person could be in various states, I1 through Ik. And then this beta of I is the rate at which a particular person can infect a person if this person was infected at time t minus I. So what our goal here is to describe the dynamics of the system by using these parameters. Specifically here that we have various regions, there is various mobility between the regions, and the infected person could be in various states. Again, K, for example, in our case, we are choosing K to be equal to 14, but K could be larger depending on as we learn more about the COVID virus. So in this particular state, the susceptible person is going to be infected at a rate beta of I, where I varies from 1 through K in this case. And this is the one that we would like to learn here. What are these rates so that we can use this information to perform our simulations and visualizations as we go forward. So what we're doing here is that we are describing the behavior of the system by using these difference equations. What is shown here, for example, what is the number of infections that rate of increase here. That's what is the left-hand side here, given by two equations, the two parameters, two equations you have here in terms of what happens to the community spread, what happens to the travel spread here. And part of that I'm absorbing here, this factor is f of qp here, is the amount of travel between region Q and P. That is amount of travel from Q to P. That's what is absorbed here. And I also have this parameter delta here, which is a contribution to the overall spread by using the travel between the various regions you have here. So given two regions, Q and P, as we understand how much travel is there, but what is the impact to the various states you have in the system, and what is the impact of the various states you have here in terms of the number of new infections you have at a particular instant of time. So we can go through some mathematics here. You can make some approximations. That's what we do here so that we get a linear system. And that's what I've shown here. We can represent this as what is the increase here as a function of the current state of the system here. And what is shown here is the beta is the variables we have that we need to learn in the parameter system that we need to learn here so that we can do the simulations based on these equations we have here. So what we did in this particular case, the mechanics that we used here is that we linearize the model. After linearizing the model, then we do the least square minimization here to reduce the error in the learning process we have here. And we also explicitly introduce one more term here, alpha. Alpha is decaying weights on the past data. This is like the forgetness factor here. so that the data that was there earlier has got less impact because this is a dynamically changing system here. We have new policies coming into picture. So we should give more weightage to the more recent data compared to the previous data. That's what is captured here by using this parameter alpha coming into picture. So let me go through some results based on this model. So what we have done here is that we modeled the community spread as well as the travel spread. We have these various parameters. So we take some various data sets available in the literature, and then we did the analysis for using at the country level as well as the state level in the US. And that's what is the results I'm showing here. So I'm just showing some earlier work we did here on by April 10th, what was happening by not including travel at that point. I'm showing here for the 3 different techniques, our techniques, SIKJ alpha is our model. The variable here refers to that for various regions, we have various parameters we use in the model. The fixed one uses the same model for all the regions you have here. And the ensemble model is a combination of these models here, but we learn the weights for us to be able to combine these models to get the results here. So, and what I'm showing here is a comparison against a state-of-the-art model that was recently proposed. This is the SCIR model, in which the COVID-19 spread was explicitly modeled in this particular model that was proposed recently. What I'm showing here is the error that is there, RMSE error and the MAPE error for the case of the US as well as US states as well as the global. What is important to notice here is that by explicitly modeling the travel, we can significantly improve the quality of the results, accuracy of these models in terms of the predictions. In the second portion here, I'm showing here what is the impact of travel data. Recall that in our model, we explicitly model the travel between the various regions we have here. I'm showing here for the US as well as the global by using the travel and using the variable model that I talked about, the ensemble model. We can get very good accuracy in the predictions here in terms of the RMSE and the MAPE error in this implementation. So we can do a number of extensions based on this work. We do have detailed results. If you visit our archive paper, we go through all these results we have for the various states, various countries. We use the data sets available and make these predictions. And how accurately they predict, in terms of the MAPE error or the mean squared error that I talked about earlier. You can get detailed results in our archive paper. So let me move along in the interest of time. So something we can do with this model is that model ultimately is an abstraction of the data. So can we measure the present by using the past through this predictions? Essentially what I'm saying is that as you evolve this model, we can look at the model at 2 different times, T0 and T1 that are shown here. We can understand how the model has evolved from T0 to T1. And we can look at the parameters of the model. For example, in our case, the beta of I, which is the infection rate from a particular state that we have defined in our model here. So what we can do is that we can take some kind of a linear combination of this beta I parameters we have in a particular region. And then we can understand here what is the impact of various policies in that region. Region could be a state, it could be a county, it could be a country. So we can understand here what is the impact of various policies on the overall spread at a particular region here. So it's one way, for example, to look at this model parameters is that we can define this metric, which is a sum of the infection rates we have for the various states for a particular region. And then we can look at the contact reduction score, for example, as a metric here to understand how this metadata has varied over a particular time. So what we're doing is that we train these models as we get more data here, the policies have changed, for example, maybe, and then we look at the model at 2 different times, combine this model parameters into a metadata, and then find it's a normalized data that the equation I've given here as a contact reduction score. So we can use this information to understand how a particular region is behaving. This contact reduction score CRS I've defined here is between -1 and +1, and higher the number, that is better. We just did some plots on this. What is the impact by comparing the model on March 21st and April 10th for this various countries here, understand how the various policies in those countries have affected this model. So keep in mind that we use the model to go back and look at what could be the impact of the policies by understanding how the model parameters have changed over a period of time here. So in this particular case, this CRS factor is the one that we used here in this particular example. Moving along, so we can use this model to our tools to be able to play with this. So we can explicitly model the travel. We can model the number of states you have in the infected states person could be in, and then we can also understand how this particular model is behaving as a function of time. So what I'm showing here is that by using these models, we can plug in these values into our visualization tool we have here, and then we can do our forecasting. We can also understand if we release, for example, certain restrictions, for example, travel restrictions, what is the impact of that? You can explicitly model that by using that travel-related parameter that I talked about earlier. So we can use that information to be able to predict what happens. That's what is the various graphs I've shown here. And this variation is what is shown here in terms of various model parameters you can choose here to be able to understand what the impact of this on the overall growth of the infection rates we have here. There's also one more work, that's recent work we have started doing in this context to understand that whatever numbers I'm reporting so far here, all these predictions are based on the actual reported cases. We know that we are not able to test completely. We do not know exactly how many people are infected, more than what may be the case with respect to what is actually reported. And that is the work we are doing here. That is the second publication I talked about earlier. This is available on arXiv. So what we show here is that we want to learn this parameter gamma here, which is the ratio of the reported cases to the estimated total cases. So we want to be able to automatically learn this parameter, and that's what is some of the experiments or the data-driven modeling we did in this context. And then the details are available at this paper. What we specifically show here is that under some conditions, we can get upper bound on this factor gamma here, meaning that we can find out how many actual cases may be there in a particular region. For example, we were not able to do this for California, given the available data for California, but for state of New York, we were able to show that the actual number of cases, the ratio of the actual number of cases to what is reported is not more than 38. So those details are available in the arXiv paper. So we give some performance bounds here as to how much can we predict in terms of the actual cases that may be. So let me move along. So let me try to summarize here what we did here in terms of using machine learning in the particular case of prediction. So we have been focused on modeling both the travel as well as what happens in the hidden states there may be in the particular case of COVID. We define those states, which are the possible infected states, and then use that information to be able to understand what are the infection rates in the system and what is the mobility-based propagation in the system. So there are two important parameters that we are learning. That is this beta of I that I've shown here, and also delta, which is also approximated in our case to get some simplified difference equations that I talked about earlier to linearize the model. These are the two parameters that we learn here by using data-driven modeling. And for us to be able to learn this, we made some approximations and linearized the model. And then finally, we used the weighted least squares to be able to estimate these parameters. So one more innovation we did in this work is to be able to use this forgetting factor alpha we called, which is intended to give more weight to more recent data here, so that's going to be used in our modeling purposes here. There's also other issues that comes into picture that I did not go into here. There are also issues about overfitting. Some of the earlier work used very simple predictions by using curve fitting. So we try to avoid the problems that comes into picture, overfitting problems. So if you look at our equations, which I did not go into some detail here, so we do deal with these problems. We also defined one more hyperparameter J in those equations. We vary the hyperparameter in the training process so that we can avoid this problem of overfitting that's potentially a problem in this predictive modeling solutions. So moving along, so we do have a prediction tool that is available at this website. Like I said earlier, this has to be carefully used. You need to provide the right inputs, data sets, and choose the models, specify what you are predicting for. So there is some parameters to be chosen here, and you're welcome to use this model, but be careful in terms of how do you interpret the results that you may get out of these models. Finally here, this is a project that we're looking at what can we do with these predictions. We are working with the Los Angeles County. We're also working with other faculty at USC, USC as well as ISI. So look into how, given that we can make these predictions, we can explicitly model certain specific features here in the context of, for example, mobility as well as internal states of infection. So we're trying to use that information to be able to accurately define these models. One of the challenges we face here is that this parameter learning scheme is a very complex process. There are various heuristics one can use. There's quite a bit of learning to be done here in terms of learning this parameter space here. And then we also said here, we're also looking into incorporating unreported cases so that we can accurately model what is the total number of infected in the population. So going beyond this, we are looking at some of the resource allocation problems in this context. We're also looking at network diffusion immunization problems. For example, we can look at the data based on where people visit. We can create a bipartite graph, for example, out of that. And then you can do some graph analytics on this problem to be able to understand what is the impact of the various policies. How does those policies affect the various model parameters that we learn over a period of time? And then use that information to go back and see how a particular policy may be or may not be working in that context. So finally, whatever we are doing here is not, in some sense, not specific to COVID. There are lessons learned from this that can be used from a broader perspective in terms of modeling these kinds of epidemics. So finally, I would like to thank the National Science Foundation that has provided us some funding initially here to look at this problem. So we're looking at both the predictions as well as the resource allocations. I also want to thank several undergraduate students who have been working with us in the last 2 months, great students at USC who have been very, very helpful to us in terms of doing this data simulation, data integration in our framework, as well as developing the visualization, the tool that I talked about, which is available now. And these are the students I would like to acknowledge for their contributions to the various portions of the software development in this project. So finally here, just looking back what we have done. So we defined a very generic model. We tried to generalize the previous models. In fact, we can show that this particular model, if you choose the particular values of the K, J, and alpha that I talked about in the model, the special cases correspond to the SI model and SIR model. So we can get various models as special cases of this model here. And our view here is the model should evolve with data. As time proceeds, the policies are changing. In fact, these policies may be changing on a weekly basis. So we want to be able to, we chose the model, we define the model so that this model is adaptive and they can quickly learn those parameters so that we can make some predictions based on the recent events that may have led to the various changes in the particular policies in a particular region here. Also, that I talked about these 3 variations of the SIKJ alpha model. These models could be region specific, for example, or based on the various similarity between the regions. We can define some common models. We're looking at these kinds of ways of generalizing the model here. And also based on this, we are trying to generate ensemble models, generating models for states, for example, and combining them for the whole country. So we believe these ways of combining models can give a better accuracy in terms of the predictions. So let me stop here. Thank you very much. I'm ready for any questions there may be.
Fantastic. Thank you so much, Dr. Prasanna. Our team has had the distinct honor of watching this presentation 3 times now, and we are learning something new every time. Can you remind us again, are any of these models available to the public for experimentation?
Yes, we do have those models available. We have put them on public domain. In fact, we are comparing the performance of these models with other models in the literature, including some of the online models in the literature. We've also integrated this with some data available from Johns Hopkins University. I did have an earlier slide where I talked about a link to that model. So if the model is available, people can play around with this model. For example, you can define your model parameters, you can choose your regions, you can choose the particular data that we want to use. And as I said earlier, we're also working with various agencies, including Uber Media, for example, to be able to take whatever data is publicly available or can be shared with us. We're integrating them so that these parameters we talked about in the model in terms of mobility can be explicitly modeled. The only thing I want the audience to be careful of is that this is a model in which you can play with the parameters. The results, what you see, the predictions depends on what the inputs you provide. So you want to carefully use these parameters and use what the meaning of the predictions means. So that's something that the reader should be careful about. Otherwise, this model is available for public use.
Fantastic. Thank you so much again for joining us, Dr. Prasanna. This was wonderful. I would like to bring back to the stage Dr. Young Lee.
Okay. Sorry, I'm back.
No problem.
This time is okay.
Perfect.
Yep, they look good.
All right, my Zoom is crashed when I switched the window. Yeah, let me continue with my talk. And actually, I think it's more better that scheduling the talk a little bit later, because just see Professor Prasanna's talk, we have touched some problems in the machine future work. And actually, our work main focus on how to model in the epidemic in the urban scale, like within one city. And from a tour again, we can see that key fact to consider about the epidemic spreading in the city, we need to consider how people move in the city and how the epidemic spread among people through contact, and finally how we can control the human mobility to control the epidemic spreading. Then I have 3 subsections for my talk. First, we can see how we model human mobility, or how we simulate human mobility in one city. And second, we need to how we model the disease spreading within the city. And finally, how we can control the take actions to control the mobility and to prevent the epidemic spreading. Let's first look into the first thing is about how to simulate the human mobility in the city. Actually, it's about the problem about a research problem of urban human mobility modeling problems. We already learned that we have some of human mobility data in the city environment, but actually we can't get full scale, large scale, or whole population scale human mobility data in the urban. Then the problem, then our solution is that since the large scale urban mobility data is not available, but we have some samples about small populations, then we can use the technology of simulation to simulate the human movement in the city. And actually, there are several existing works here to solve these problems. There are 2 categories of existing work. The first one is model-based method to like time-June model or ioHMM model to try to model the human mobility by accurately model the real-world mobility behaviors. But actually, those kind of models are usually very simple and overlook the complicated human mobility patterns. And on the other hand, there are another lines of solutions named model-free method, like mainly use the advantage machine learning method like GAN technology to propose like trajectory GAN, sequence GAN, to use the GAN neural networks to learn from human mobility data and to generate large scale mobility traces. But actually, for those kind of models, it's hard for them to capture the hidden patterns of human mobility, because those kind of model-free methods are based on the data, and the data-driven usually can't capture the patterns hidden in the human mobility. Actually, our solution is that we combine them together, combine the model-based and model-free model together, and we propose a generative adversary framework. And in this framework, we can combine the advantage of the model-free method, like we can incorporate the mobility regularity extracted from the data into the model. And on the other hand, it also combines the advantage of the model-based method, and we can learn from data to generate realistic and high-quality human mobility. And let me introduce a little bit more about the details about our framework. And basically, it includes two parts. The first part is the generator network. The generator network, we need to use design the neural networks to capture the complicated temporal transitions of human mobility, and also need to model the effect of the urban structures that determine how people will move in different regions of city. On the other hand, we design a discriminator. The key goals of this discriminator is to distinguish the generated data and the real data, and try to tell us is this trace is a generated one or a real one. For the details of the generator, including 2 LAT. The first one is the sequence LAT. The sequence LAT is use a self-attention-based network to capture the complicated temporal transitions between mobility. Like when you move in one day, you start from your home and go bus stop and then go to work, and then also with some other short stays in the city. And on the other hand, we have another network of RegNet. The RegNet is try to consider the location influence that you also use attention-based network to model the effect of the urban structure on human mobility behaviors. Overall, the generator network use a sequential network to capture our transitions between different locations of the city, and use the RegNet to capture the complicated urban structures. On the other hand, the discriminator of our generation network is try to build a simulated embedding component to open the features of the human mobility and use a multi-conventional unit with different size field to process the feature metrics. And we can see the network design is a little bit simple, but the key goal is to try to distinguish the generated data and real data, and can tell us the truth by the loss function design here. And finally, we combine the generated network and discriminated network, and we use a small scale populations like 1,000 or 10,000 of people's mobility traces into the model, and the model can learn the patterns of those traces and generate large scale population mobility of a city, like several tens of millions, like in Beijing city. Yeah, for the network training, we use reinforcement learning based training to reinforce the system to converge into a stable systems where the Monte Carlo search algorithms. And moreover, we also use the very powerful mass technology of pre-training networks to component with the mobility regularity tasks. Like for the generation network, we use the regularity extract from the mobility to pre-train the generator, and also for the discriminated network, we also pre-train the network with the use of mobility regularity. And after model design, we use two real world data sets. One is from mobile operator of Shanghai, and another is JUNIF, is open data set. And we design different kind of metrics to evaluate the realistic of the simulation, like including the mobility distance, mobility radius, durations, how many locations you have visited one day, or the rank of the different kind of locations. And we combine our method with the meshing method, including model-based method, model-free method, and some other mobility prediction method. And our result is here, and we can see from the result that the model-based method is always performed well than on the mobile operator data set. And on the other hand, the model-free models, for example, the second scan, it can all performs well with some of the metrics. But actually, the problem is that they can only capture the human behaviors on only several limited kind of metrics, and our model, on the other hand, performed best on most of the metrics on those two data sets. And we can see more details about the performance. And the key idea shown here is that from the generated distribution of the generated data, we can also see that our generated data of human mobility is more consistent with the real data. And from the visualization level, we can see how our generated data of the in the aggregated population level or the individual levels, we can see both that the spatial distribution of the generated aggregated population distributed in the city are consistent with the real situations. Yeah, this is the first task we need to do. We try to use generate a discriminated network to generate high quality human mobility. With such kind of data, we can know how people move around the city. And the second task is that use such kind of mobility data, how can we simulate the disease spreading across the city? And as I introduced before, I will already introduced by the two professors before, For the epidemic modeling, we have basically two approaches. One is the simulation-based approach, and another is mathematical modeling. And here the problem with the simulation approach is that it only can simulate a specific disease and have low stabilization for the parameters, and the simulation process is also time-consuming. Then we take the second approach of mathematical modeling. For the mathematical modeling is also use the most famous model is SER model as introduced before. And I just ignore the details here, but the problem of the current model is that it can't take
Ooh, I think we might be having some technical difficulties. Maida, how does this look on your end?
Yeah, I don't hear.
It's
We're
frozen.
having some problems.
It's frozen.
Okay.
I'll try to call him.
Okay, fantastic. So we'll give this maybe 30 more seconds and then we'll take it from there.
If need be, we need to move on, I think.
Okay, got it. So Dr. Wang, Jianmin Wang, are you there? I would like to welcome to the stage, if you are, Dr. Wang, the Dean of the School of Software, the Vice Dean of School of Information Science and Technology at Tsinghua University.
I'm here.
Fantastic. Are you
Yeah.
able to share your screen with us? There you
Okay.
are. Great.
Okay,
Thank you for jumping in early.
thank you.
Of course.
Yes, let me share my screen first. Can
Perfect.
you see my slides?
Yes.
Yes, the full screen.
Perfect. Looks good.
Okay.
Thank you.
Okay, dear friends from here, USC and THU, and good afternoon for the friends from USC, and good morning for THU. Yes, it's my great pleasure to share our work, open source database, Apache ioTBD for Internet of Things. Yes, I think the previous speakers say a lot of things about the pandemic. I think after the pandemic, after our lifted the lockdowns, we will reproduction. So I just think say something about the industrial internet. You know, we are now at the internet 4.0 area. The data plays an important role in industrial digital transformation. I think the data in the industry is an old story. I think from the 60 years ago, we built an enterprise information system. We collect the data from design to production. We call it enterprise data. And in recent 10 years, the machine connected to the internet and be digitalized. So the machine data come to the enterprise data domain. So nowadays, the machines are generating data and consuming data in the industrial Internet of Things. You know, traditionally, we collect data from the edge devices, from the equipment, and send it back to the data center in the cloud. Nowadays, we just enter the 5G age. So we have the control data from the cloud to the edge. is a closed loop for the internet application for the machinery controls and the production. So the machine data is a big problem for the new area, for the modern industrial domains. So you know the PLCs and the sensors collect data points attached with timestamp all the time from the edge devices. How to manage machine-generated time series data become a key issue because the volume, the speed, the velocity, the diversity that the machine-generated data it produced day by day. Let's see the definition about the time series in academic community. The first, we said the time series is an ordered sequence of values of a variable at equally spaced time interval. This definition is defined by NIST. Another definition is a finite or unbounded sequences of data points in increasing order by time. It's not required the time series are equally interval. So I think we will use a later definition. Nowadays, along with the rise of Internet of Things, time series management are hot topic in academic community. You can see we just get a glance at a survey that published by TKDE, I think 2 years, more than 2 years ago. There is a lot of different systems are produced, are developed with different goals, such as compression, get a high write throughput, or for some specific query. We can get some several classification criteria. You know, first is internal stores. That is time series management system has its own storage engine. They have internal structure. The second category is external stores. They just store the data with a big file system, big data file system, or other distributed systems. We call it external stores. And the third category for the time series management system is just a relational database management extension. Our Apache ioTBD is internal stores categories, belongs to these categories. There is also a lot of time series database system for IoT in the industry community. The upper two just build the time series management built up upon the relational database management system, such as open source. We just use open source PostgreSQL directory, or be based on a special layer to with some auto-sorting or with some query optimization techniques upon the PG, PostgreSQL. The upper two are based on the RDBMS. The lower part, the lower two, based on the big data systems. such as the first one is we just use HBase or Cassandra to store and management the time series directly. And also someone build some time series data management system over the HBase or Cassandra, such as OpenTSDB or KerisDB. This is our open source project, Apache ioTBD. We position our product on the database for Internet of Things. Is an integrated data management engine. Next, we will explain what the integrate means. Designed for the time series data collection, storage, and analysis in the industrial IoT scenario. This is our goals, our mission. It's initially developed by our school and the Big Data Research Center at Tsinghua University at the autumn of 2015, 5 years ago. And we donated to Apache Software Foundation in November 2018. Yes, you can find it in this website. Yes, what's new for the data management in the industrial IoT scenario? Why we build a new wheel? I think there is 3 reasons for us to build this project. First is data schema. In the IIT application scenario, data schema, it from the schema first to schemaless. As you know, we just learned the database course, most based on the relational model. We see it schema first, or it management the structured data. And the schema, when we want to storage the data from the application, we must design the schema, design the table. We must define the table first. Yes, it is to say that defined by the DBA, from the entity relationship model to relational normal form model. That is to say that schema defined by the backend, by the cloud, and the schema changed seldom. Yes, it's stable. But in the IIoT, we need schemaless. The schema defined mostly by the front-end devices. What the conditioners or the meters should be stored, it just produced by the end devices, not defined in the backend in advance. And the schema changed frequently because we will update our protocol frequently when we find some fraud and we find some new requirements. So it's the first difference from for the IoT data schema. Another one, data schema in the traditional database is smaller. We must, I think, in the enterprises, we define thousands or 10,000 of tables is a big one. But in IIoT, we defined a lot of time series. As you can see, each equipment, we need a schema to describe it, especially for all the meters, all the sensors attached to the equipment. We need also a metadata to describe it, so it need a schema. So the data schema in IoT has a large volume and changed frequently. As I said before, the data defined by the terminal devices. Different devices have different meters. So when the machines are used in the real scenarios, the schema may change frequently. For example, the meter for speed may be for a data type to float. We get more accuracy measurement. Maybe the protocol can be upgraded. Let's say that at the first, the machine just collecting 5 work condition meters. And then we want to collect 10 meters on the device. So the volume, the data schema, or the data metadata may be changed frequently. So the data schema in the IoT scenario should be also considered as data because it has a large volume and change frequently. So in Apache ioTBD, the schema can be defined by the backend and by the front end. So let's say that means ioTBD does not require the predefined schemas when the edge devices want to send the data to the cloud. It's very convenient for the end devices developers. So I see it as a data spring, not database. The spring, the water, it must flow from the sources, and the cloud must collect it whenever and what type it is. So the ioTBD can infer the data type at the backend and manage the scheme as data. That means ioTBD can manage a large volume, tens of billions metadata, tens of billions of time series. So it's a challenge for us to tune its parameters for better performance and persistent data and serve for query and analytics frequently, efficiently. Yeah. So this first challenge. The next challenge for the IoT scenario for the time series data management is data processing flows. For the traditional time series data processing flow over the industrial internet, we know we encode and compress working conditions of the meter data first. Then we send it back to the cloud with our own protocol. And then we deploy the message and decode and write to the disk. So for the edge, for the terminal end or the front end, the number of edge devices increased quickly. And we know the Internet of Things are very popular day and day. And in the backend, in the traditional processing flow, there is a long processing chain. It affects the real-time requirements. And in the cloud, we have a heavy workload. And nowadays we know the computing power increased quickly in the edge. So we considered how to take advantage of computing resource in the edge, and so that break the bottleneck in the cloud. So we have a new strategy, writing TS file, writing the monitor, the meter data in the front-end device directly. And just you see the traditional process flow, our solution. We just invent a new time series zip file. It's a compact with compact format. In the edge devices, we persistent writing the data to the TS file only once. Then we transfer the TS file directly to the cloud. First to our ioTBD with a query and analytics engine for the time series data. Another one, we also embedded TS file and imported it to the Spark, to the TensorFlow, to Hive, to the open source, big data analysis and processing software. So it's our solutions. It may be reduce the cloud processing time and energy consumption. So it is our TS file, a time series native columnar file format. You can see we have some advantage with a high compression rate and has time series synopsis info for quick query and analysis, and reduce the transcoding cost in the cloud. So it's our the second features or advantage. The third and the last, what's the new for the data management in IoT scenario? I think there is a different data usage for the IIoT applications. Apache ioTBD have a lot of built-in functions for both query and analytics. I think the first traditional time series data engines, just for raw data query, just for time value range filter, for time dimension aggregation. But in IoT, with a new downsampling algorithm for multi-granularity data. As you see, a lot of data for the in IoT just for monitoring. The screen has its fine defined resolution. We must sampling the data point according to the screen, and not if the more than data than the screen resolution, it's no use. The second is a time frequency transformation. You know that IIoT scenario, we just managed the cyber physical system, a cyber physical system. There is a lot of physical loss in our machine or in the work conditions. So we need the time frequency analysis for the signal processing. The third one is a pattern matching. Yes, you know we just want to find some of the regularity from the time series data. So,
Professor Wang, excuse me, we are running a little late. Can you please wrap up soon?
Okay, I will go fast. Yes, it's a pattern matching. So the ioTBD has 3 features for the new challenges. So we have integrated our Apache ioTBD with the ecosystem in the Apache or open source ecosystem. Yes, now the Apache ioTBD community grows very healthy and very fast. Due to the time, I will omit it, and has some applications and users in China. You can see for the transportation, for the device monitoring and the platform, for the manufacturing, and for the community users. Yes, also for the overseas users, such as Programmatic Minds, this company located in Germany. Yes, we have also some application example for Shanghai Metro monitoring, for Tianyuan equipment maintenance and operations. Yes, it's my great honor to present our work here and welcome you join our open source community. Thank you.
Thank you so much, Dr. Wang. We truly appreciate you being here. We truly learned a lot. Thank you so much.
Thank
Now
you.
I would like to welcome to the stage, thank you, Cyrus Shahabi. Thank you. Dr. Shahabi is the professor of computer science, electrical engineering, and spatial sciences, and the chair of the computer science department here at the USC Viterbi School of Engineering. He is the director of the Integrated Media Systems Center and the Informatics program at USC School of Engineering. Dr. Shahabi will present today on PrEP, Pandemic Risk Evaluation Platform Beyond Contact Tracing for COVID-19. Thank you, Dr. Shahabi.
Thank you. So can you see my presentation screen okay?
Yes.
All right. So let me basically start by trying to make sure that we're all on the same page as far as what we call contact tracing. So by now, I think, unfortunately, we're all familiar with these terms. The first term is the incubation period of a virus, which is basically for COVID-19 is about 5 days. This is the time that from the time between infection and when you start seeing symptoms in the patient. Then we have the generation time, which is the time between getting 2 people, in, one person infecting another person. And with COVID-19, the generation period can be shorter than the incubation period. That's why we see these pre-symptomatic transmission. Because of that, it's becoming even more important to do the contact tracing quickly. And what we mean by contact tracing is basically, this is a traditional approach that usually at the beginning of pandemic people use to prevent pandemic, but right now we are looking into this as an approach to keep the curve flattened or hopefully even stop the pandemic if we do it right, which is basically interviewing a confirmed case, somebody who's positive, and find out during the past several days, for COVID-19, it can be from 5 to 14 days, what other people they were in contact with, so that we can inform them and then potentially isolate them or put them in quarantine. Now, the challenge is that this traditional way of contact tracing has some shortcomings. One is that you're relying pretty much on the patient memory to remember things, who they met, at what time, at what location. It cannot be scaled up. So as I said, this is traditionally used at the beginning of the pandemic, where you have a small number of cases. If you have a lot of cases, especially in the middle of a pandemic, this is going to be challenging to do it at scale. And then based on a paper that actually here, you see a figure from this paper that I'm citing here from Science. It came out in April 1st and actually used the data from Wuhan, China. And they showed that if you look at the how many people you can basically, the percentage of success in finding the people that you can isolate, and then from those you go and find their contacts, and you put their contacts in quarantine. There is a kind of a sweet spot, this green area, which is the rate of production rate R goes below 0, became negative, and that's basically how you can stop the pandemic. And they showed in that paper that if you basically be able to quickly isolate people, this no delay situation, then suddenly you have a larger green area. So basically, even if you have a small number of people you can isolate, and I tell you why that might be small, you still, if you quickly reach out to, like, say, 80% of their contacts, you're still going to be in this green zone. Now, why we might not be successful in isolating people? This is because of the pre-symptomatic cases, because you usually interview folks when they are symptomatic, or usually test them when they're symptomatic. But in the case of COVID-19, there are a lot of cases that are not symptomatic yet. That's called pre-symptomatic. And because of that, you might not necessarily be able to immediately isolate all the contacts of the confirmed cases. So because of this paper basically argued that in order to do this no delay, which is a very low latency in contact tracing, you need to do it in a digital form. So that was basically the main justification to do digital contact tracing, which is basically means that you use your people's mobile phone to know where they are and who they're in contact with. And this would actually not only solve the latency problem, but it's also help to scale up the contact tracing, and also address the patient recall issue. So because of that, for the past several months, we witnessed a huge number of apps that are out there that they promise to do contact tracing. Here is a quick table provided by my colleague here at USC, Professor Krishnamachari. But what I want to emphasize is the most famous one, I guess, the one that is being proposed by Google and Apple. And just to tell you briefly what the idea there is, that is if two people are close enough that they can transmit the virus, the idea is that their phones are also close enough that using Bluetooth signal, they can exchange a key. So imagine each person has some sort of a unique key that they can exchange. Now, if one of these two later become sick and become a confirmed case, this person can release all the keys that was kind of collected on or send out, sorry, from his phone to everybody else that they're in their proximity, and then everybody else can check. And if they see suddenly that on their phone they have the key of this person, that means that at some point in time they were in contact with that person, and therefore there's a chance that they might also be infected. So this is the approach that was proposed, and as you see, actually it hasn't yet been developed because there are a lot of obstacles and disadvantages actually to the approach. One, limitations, I should say. One is that this approach, of course, would not take in the transmission through objects into consideration, because the person might already left, but the objects there might still be contaminated. It doesn't take care of the situation where you have, for example, indirect transmission. What we call indirect transmission is shown in this figure, where Alice meets Bob, and then Bob is infected. Alice is infected, meeting Bob, and then Bob later meet David, and David can get infected also indirectly from Bob, even though Bob is not yet symptomatic. And this is again this pre-symptomatic issue that can be prevented if you have these traces of the movement of Alice and Bob and David, but it cannot be prevented if you only rely on these pairwise contact that Google and Apple propose. These are some of the practical limitations, but they're also by design, there are some challenges. One is that potentially you will see a lot of false positives because two people might be close enough for their Bluetooth phones to exchange data through Bluetooth, but not close enough for them to transmit the disease. So potentially you can have a lot of false positives. That is a challenge because usually you use your app to get information when you need it. But if your app keeps sending you notification, at some point you just turn it off, right? So a lot of false positives might result in you basically coming numb to the notifications. But there's also a deeper, problem with this approach, and this is this is a fully end-to-end approach that only rely on the app. Basically, the entire contact tracing is conducted by the app without any human contact tracers in the loop, and that's a challenge. That's a problem, major problem with the design, and you basically need to have the human contact tracers in the loop, and you also need to collect other source of data. The contact tracers probably would collect this data that can inform policy and spread models that we heard throughout the day. With this approach, basically there is no extra data that can be collected. Even the contact information is really not collected in a centralized manner. So what we are proposing is basically going beyond this approach. I mean, definitely the data is interesting and useful, but we can also collect other source of data, especially location data, the duration of the contact, the traces, as I mentioned, that basically the trajectory of people moving. And the idea here is that if you collect all this data, you can go beyond just giving alerts. You can actually calculate some sort of a risk score between, say, a number between 0 and 1, where the higher the number, the higher the risk score. And as I show you later, this actually can be used to isolate. People can self-isolate, self-quarantine if their risk score is high. You can basically suggest people with a higher risk score to go and get tested if you have limited number of tests available. And you can also use these risk scores to identify hotspots, and of course you can do contact tracing as well, but also you can use this for identifying hotspots and then inform spread models that we heard throughout the day. This risk score can also help improving those models. So this is basically what the framework we are proposing. Is a little complicated, so I'll just show you through one step at a time. Basically, this is the app. The app collects these location and co-location data. The co-location data is the Bluetooth data that I mentioned. And the idea is that once you have this data, then you can send this to some sort of a database that basically can perform spatial-temporal analysis, where this can be used by health practitioners to do the contact tracing by finding if two people were at the same location at the same time. And then this is basically where the health practitioner can identify the confirmed cases, and these are all stored in secure databases. And analyzing this using various machine learning techniques, you can calculate the risk score. So this, in addition to the spread analysis, some of these models, for example, that we heard today, can basically inform policymakers to intervene, and their intervention can basically be a loop that can improve the situation, as, for example, you put people in quarantines, close spaces, decontaminate locations, and so on. The risk score, the risk analysis can also, as I mentioned, create this risk score that can be fed back to the application, so the app users can actually see what's their risk score, and they can change behavior based on their own risk score. So we are in the process of building this from using various sources. We already built the app in collaboration with one of my colleagues, Peter Kuhn. We also got funding from NSF RAPID program that basically give you quick funding in response to certain emergency research, in this case, the COVID-19. Where we focus on how to collect these location traces and durations, and how to do this spatial-temporal analysis to identify not only direct transmission, but also transmission from objects, contaminated objects, as well as indirect transmissions. We also, under the same award, we are looking in various way of risk analysis to calculate the risk score. This can be based on the risk of the individuals that you're in contact with, the risk of the locations that you visit, how long the contact, the actual location of the contact, the social strength of contacts, because if two people are socially related, either, for example, they are friends or family, there's a higher chance of spread of the disease. And you can actually use some of these trajectories and historical data to infer the social strengths in order to calculate the risk. I'm not going to talk about our spread analysis. This is very similar to many of the models that people discussed already in the past couple of presentations. This is just our version of spread analysis. The model is based on mobility and movement. And the idea here, though, is that once you do the analysis using our model or anybody else's model, you can then define intervention strategies. For example, if somebody's risk is higher than 0.8, then this person should be quarantined or isolated. Or if a location risk is greater than 0.9, then this location might stop admitting people. And then by implementing these interventions, you can look back to the model and see whether you can reduce the number of infections or you can reduce the risk. So that's one little difference from what we are studying than the presentations you've seen so far. We're also building various dashboards. We are hoping that USC would basically adopt some of these techniques. We're working with various committees to see if that's possible. For example, as I mentioned, we are working with human contact tracers. So the data can be only accessed by the human contact tracers, and they can quickly identify if two people were in contact using the trajectories and traces. This is another dashboard that I mentioned that for the policymakers, that they can identify hotspots immediately based on the people that are infected and how they moved. That can also be used, for example, for both decontamination and also to check the density and say certain classroom has higher density than was expected, and then you want to reduce that for the next future days for future classes. Of course, by now you already worried about the security and privacy because we're collecting location data, we are collecting content data. So these are some of the considerations that we also have in mind when designing these things. Everything should be based on consent and voluntarily, opt-in. It should be transparent. We should minimize the data collection. Everything should be secure, and so on. So we basically have all these, we're collecting various articles, and we try to make sure that we have this consideration as we design the system. Just in particular for privacy, there are many ways that you can address privacy issues. The simplest way is that location traces can basically store locally only on your phone, and then users have the control to decide at what frequency the locations should be collected, at what precision the location should be collected, and maybe even redacting certain locations if they want to keep it private. This is actually interesting because a lot of privacy sensitive locations, like for example, your home or places that you're only in contact with family, for example, those are less of an interest to our risk analysis. And actually conversely, the places that are public, like a shopping center or a classroom, those are less sensitive as far as privacy goes, but actually more important to our risk analysis. So in a sense, actually privacy and some of these data collection may not be in conflict. We also look at some two-stage iterative approach where you collect the data and at certain resolution, and then you give a feedback to the user that if you share a more accurate version of your location, that would suddenly increase the number of people that we can help by a factor of 2 or something like that. And that way you incentivize people to give you more accurate information as another way of dealing with privacy. Of course, there are more sophisticated approach for privacy, including doing things in an encrypted space, perturbing location, and so on. That these are various grants that we are actually have already, not related to COVID-19, but very as far as the grant goes, but the topic very much relevant. And any of these we can be leveraged also in this project as well. This is actually my last slide, so I can stop now.
Fantastic. Thank you so much, Dr. Shahabi. We truly appreciate you being here.
Sure.
I would like to welcome now our final presenter to the Zoom stage, Professor Jun Zhu. Dr. Zhu is a professor in the Department of Computer Science and Technology at Tsinghua University and the director of Basic Theory Research Center. He will be presenting today on deep probabilistic programming. Please join me in welcoming Dr. Zhu.
Thank you. So hello everyone. So it's nice to meet you on this conference. So I'd like to introduce some basic idea about probabilistic programming and especially the deep, the progress on the deep models. So I would like to start with some motivation. So so there are several nice work, a nice talk on the COVID-19 prediction. But when we do the data analysis, we need to consider some uncertain factors. So including like for the event itself is uncertain. And also if we want to read the image like CT images, even for the same person, the image may be taken in different time, also have a lot of variance. So in this case, we need to consider these kind of uncertain factors when we make a reliable prediction. In some cases, actually, the uncertainty may be worse. So here is a simple example, like for image recognition. So actually, once we impose some small noise on top of this image, as I show on this screen, actually for human eyes, it's even like we cannot detect this noise easily, but this noise is sufficient to fool a deep network like the popular network, the AlexNet, VGG, or ResNet, with a high confidence. So this is actually another evidence that we need to consider uncertainty when we do the analysis. So another type of uncertainty is less well known is from the model side. So currently the trend is that we increase the size of model. So from like a billion to 10 billion or even more parameters. So but at the same time, we need to consider the amount of information we have to train this huge model. So in fact, from the information theory, the amount of useful information increased actually much slower than the amount of data we have. So so as you can see from these different type of curves, so so we can in most cases we need to be very careful about the potential overfitting. So in that case, also the model can have a huge uncertainty because for given data, you may have a multiple model to fit them well on training, but they may perform quite differently on testing. So this is kind of a model uncertainty. So you may say that the deep network gives us a probabilistic output, Py given x. So does it enough to capture the uncertainty? The answer is no. So if you purely use this output probability, actually it's a kind of over optimistic. So here's a very simple illustration. So suppose we have a training data in the white area. So we can use the training data to fit a curve. So in some kind of sense, in some sense of like a very good fitting. But if you want to do the testing for the X star who is far from the training area, so you can see that in the traditional method, you predict with a high confidence that there should be kind of some intention of this curve. But intuitively, because this data is far from the training data, so the uncertainty should be high. But the current model doesn't consider that. So we need to some kind of a more powerful method to do that. Actually, in machine learning, there has been a lot of work on the probabilistic approach or even Bayesian approach to do the uncertainty modeling inference. So the core idea is quite simple. They use like a so-called Bayes rule to do the inference, to calculate the posterior of the model in some space by considering the prior information which is encoded as a prior distribution, and also the data which is encoded by a likelihood model. So this is a general principle, and there have been a lot of work, a lot of progress, even in this deep learning area. So so if you're interested, you can read this Nature. This is the Nature Review article about the field. So today I'll talk about probabilistic programming. So the goal is to make these kind of probabilistic models to be easily used, programmed, and manipulated, so automatically. So here is one example from the traditional model. So I use Stan. Stan is a very popular probabilistic programming library developed in Columbia. So this is on the left side. So it's a very simple linear regression model. So you have x, y, x as the input, y as the output. So it's defined as a linear function, and plus some noise. So the noise can be white, like your normal. And in this model, you essentially define a process, a distribution of y given x as a normal. But if you use like a Python or C++ to program this model from scratch, it can be painful, and also you need to tune every part. But probabilistic programming actually makes this the implementation of such models to be very intuitive and easy. So as I show on the right side, so in the Stan library, you can define your data, so including the number of points, the dimension of the feature, and also you define a parameter, including all the parameters you consider for this model. Then you define model with normal. So normal is already implemented in this library. So you just define, you just program as you write the general process. So very intuitive for this simple case. So everyone knows deep learning. So the recent progress for the probabilistic programming also get conjoined with deep learning. So there are two directions. One is that you can use like a Bayesian inference to do better deep learning, to essentially to capture uncertainty. Another way around is that you can use a deep network to make the traditional Bayesian model to be more powerful. So this is like a two-way marriage. So this is if you look at the history, actually there has been a lot of work, even in the like the first generation of deep learning. So in that time, people just call neural network. So I just give you two examples. So this is a PhD thesis by David McKay and supervised by John Hopfield. So it's about the Bayesian method to do inference for neural network. So at that moment, we have much less data and much less powerful computers, and people cannot like fit a larger network. So usually, even for a shallow network, it's easy to get overfitted. So at that moment, the Bayesian method was studied to protect this this neural network from overfitting. And actually, they have a lot of very nice theoretical analysis there. Another example is from Jeff Hinton and his PhD student, Rafi New, and also using Bayesian learning to protect neural network. Actually, they also have some nice theoretical results to show that for some kind of Bayesian neural network, if you, on some conditions, actually it's equivalent to some stochastic process called Gaussian processes, right? So more recently, actually, even for the like some popular method like dropout for deep networks, actually they have a deep connection with Bayesian inference. So this here is one example. So dropout actually equivalent to do some approximate Bayesian inference for deep Gaussian process. And based on that understanding, people develop some better method to estimate the uncertainty for prediction. So it's so-called Monte Carlo dropout. And also to search for the architecture of networks, there are also some nice work recently, try to using a Bayesian approach to consider the uncertainty of the structure. And they even define a stochastic process to generate the structure of a network. So here's one example, including like how many layers, how many neurons for each layer, and how the neurons are connected. So this kind of architecture configuration, so they can generate different type of models. And in another way, so people use deep learning to, particularly deep neural network, to make the Bayesian model to be very powerful. So here is a very high level illustration. So we know that for some simple variable, like a uniform or stand normal. So after you use some function transform, actually you get another random variable. So whose distribution is much more complicated in the sense that you can use you can like using a data-driven approach to guide the learning to find a proper function, so represented by a deep network, actually make sure that the transfer variable the distribution can match a real data distribution. So this is really powerful. Actually, we have seen a lot of examples. For example, using the GAN network, even in the purely unsupervised learning, we can learn a network, can transfer even some white noise to the nice looking natural images. So this is really a very powerful paradigm. So we have seen examples like a version autoencoder or GAN network. So technically they belong different category. So versional autoencoder is kind of implicit model. They define the data generating process with some density function, but GAN is another category called the implicit model. They just define the transformation process to turn some seed to a natural image, right? So there have been a lot of work in machine learning try to learn such models. So we generally consider two types of algorithm. One is called versional. So essentially we turn the inference as a optimization task, and then we using the optimization tools to solve this problem. So this kind of method is efficient, but it's naturally has some like approximate error because during the optimization process you introduce some assumption about the possible distribution. So this may introduce some errors there. Another type of method is called the Monte Carlo method. So it's to simulate in some space by defining some Markov chain. In theory, this type of method is accurate as long as you run it sufficiently long. But in practice, it's kind of low efficient in terms of speed. So you may need a lot of run to train to run the simulator. And another type of low efficiency is on the particles. So in the random sampling, in some cases, especially in high dimensions, the particle may collapse, may degenerate to have low efficiency. So there have been a lot of work to improve that, including to make this algorithm to be scalable and also to be more accurate in high dimension. So that's a background. I hope you know you can get the idea that this kind of methods are powerful and they provide a very powerful language to deal with a real problem. So now I turn to the programming part. So you may also get the idea that this kind of model is kind of more complicated to deal with compared to deep network. But the good news is that we already developed some library to support the programming of such models to make the algorithm to be automatic. So I draw an analogy comparison to the deep learning library. So I guess you know the TensorFlow, PyTorch, and in China we have PyTorch and some kind of library to program the deep networks. But for these probabilistic models, especially when we deal with the deep networks, we also have the corresponding library. So I introduced one developed in my group called Zhusuan. Zhusuan is a Chinese name, so the English name is Abacus. So it's kind of probably the oldest calculating machine we have. So here's how we develop this model using the library. So here's the modeling language. So on this library, you define model. You just build a model. So the model is represented by Bayesian network. It's essentially a directed graph. So on the graph, you can define each node as a random variable or a function or some neural network. So we have a random nodes and also deterministic nodes. Then you retain a Bayesian network. So you within this scope, you can define your model. You can just draw the graph, right? So by you add edges to connect them and define the dependence. And for probabilistic inference, the one tricky part is that, so we define one model, so like the most left part. So we would like to do multiple query, multiple inference. So the inference means that we observe a part of the variable and we ask the question to infer maybe the posterior distribution of some unobserved variable, like the white one. So for the same network, we can do multiple times of inference. So like the graph on the right side. So in this case, traditionally you may need to encode each graph separately, but on our library we can reuse the model defined on the left by using the a decorate called meta Bayesian network. So using that, actually you just build the model on the left side for once, then you can reuse for multiple times by giving different observations and do the inference. And for the algorithm part, so we support the state-of-the-art algorithm, including version inference. I apologize for some Chinese here, but essentially the top row is for versional inference, the bottom row is for the Monte Carlo method. So essentially we support the state-of-the-art algorithms, including the stochastic gradient method to estimate the gradient from the a large batch of data. So we support a different estimate of a gradient. So including some spatial design for the discrete variable. And for Monte Carlo, we also support a stochastic gradient Hamiltonian Monte Carlo, and with even some predicate conditioning variants to make the efficiency to make the efficiency to be high. So so we also have a model rule. So essentially we implement some popular model in this direction. So including like a topic model or metric factorization method, and version loading encoder, Bayesian neural network, deep belief network, Gaussian process, and so on. So we also have different ones for symmetrical learning or different kind of applications. So this is the open source project. So so you can find the source code on GitHub, and we also have a white paper to plan the more detail about this library. So on the right side, I just list some recent work we developed in my group about the even better algorithm and also some applications. I think I'll take a few minutes to give you some quick example why this kind of methods are useful. So first one is for temporal prediction. So I think this is maybe related to the COVID-19 prediction. So you need to consider the temporal dependence, the temporal dependence of the data. So essentially we consider a air condition prediction task using the LSTM model with some attention mechanism. And so this is a baseline model actually provided by some companies. They come to my lab, try to using the Bayesian inference to calculate the prediction interval, essentially uncertainty interval. And meanwhile, we found that actually using Bayesian inference, we can dramatically decrease the prediction error. So as highlighted in dark. So another example is that in many cases we may have like a few label data but many unlabeled data. So symmetrical learning is kind of a useful setting to extract the information from unlabeled data to help us learn a better classifier. So essentially we use the GAN framework to extract information from the unlabeled data by learn deep general model, and then we use the extracted information to help the classifier building. We develop a so-called triple GAN, essentially GAN theoretical paradigm with 3 players, and we can theoretically show that this conjugate to the target distribution, and also practically we found it's much better than the other variants of the GAN network for symmetrical learning. So another interesting case is that because we can calculate uncertainty of predictions, in some cases, if the data is of low quality, we may have a low confidence prediction. In that case, we would like to reject the the uncertain cases, but we can do more by using by building another deep network to transfer these uncertain cases into some high density area. So in that cases, the transfer data can be predicted correctly with high confidence. So as you can see from these handwritten cases, like for this input is it will predict wrongly as a 9, but with the certainty also low. But using the deep general model, we can transfer this data to another 5 image, right? So once you input this transfer data to the classifier, they give you a correct label with a high certainty. So this is the general idea. So overall, you can using this kind of mechanism to improve the final accuracy of your prediction. And the last one is about the robustness of against voice noise. So as I said at the very beginning, if you don't consider the voice noise, actually you can be vulnerable to this kind of attack. But here is one example that we can use a Bayesian inference principle to learn a representation space with optimal robustness. We can show theoretically, and also from that understanding, we can design a new objective to guide the training of this network to make sure that the trained network is robust against the noise. And so as I show on the left side, you can see this is the representation learned by the original the vanilla deep network. By using the new training approach, you can have a better representation in the sense that it can be more robust against the voice noise. And here's some example of the noise we find. So to quickly summarize, so the message is that uncertainty modeling and inference is critical for AI applications, and the Bayesian deep learning provides a powerful language. And also we have some library to support this kind of models algorithm. So in particular, I introduced the JUSON library and give you some quick example about the security prediction, central learning, and also advanced robustness. Thank you. So stay safe.
Thank you so much, Dr. Zhu. That brings us to the end of day 1 of our USC-THU Symposium. We hope to see you all again tomorrow as we dive straight into 7 of our esteemed presenters at both campuses. Presenters, please stay on so we can take a quick picture of everyone. For everyone else, good night to those in Los Angeles. Have a great rest of your day to those in Beijing. And as we say here at the University of California, fight on.
Fight on.